Welcome back. This module is about text representation. In this module, we'll talk about converting text into different formats that can be consumed by machine learning techniques. First, we'll look into the theoretical background and then we'll implement it through the code as well. So, machine learning techniques require highly structured data, a data that is being organized in the form of a table or a matrix that has got rows and columns. In the case of textual data, the rows represent documents and the columns represent unique features. Each document is going to hold a value for these features. In case of supervised learning, the last column represents labels. Otherwise, in case of unsupervised learning, this may not be provided. So this structured data is being provided to the machine learning techniques as past cases and the model is being constructed. Once the model is ready, it can be used to predict the label for any unseen document. Our task at this stage is to convert the unstructured data into a format like this. This process is called vectorizing the data. So if you are given a data set like this, the target would be to convert this data set into this format where we have got documents from D1 to DM and unique set of features from T1 to Tn. Unique set of features is also called vocabulary or dictionary. Once the processing is being performed, this data set can be converted into a structure like this. This is the desired structure that we can provide to the machine learning technique. As you can see, we have got the rows as documents and the unique set of features as columns. Each document has got a certain value for each feature. In this case, the value represents the frequency of occurring of this feature in this document. This is one way of representing this data set into a structured format. There are other representations as well that we'll look into in a while. One of the important things to consider over here is that this representation is following a bag of words approach. A bag of words approach is the one in which the position related information is lost. For example, once we have converted this document into this format, there is no way we can reconstruct this document from this representation because we do not know where this was placed in the document. We know that it was present once, we know that there was an is, we know there is a, but there is no information about the position. We on purpose lose the position related information because that is going to make the case a lot difficult, and we are going to have a lot many features and too few representation for these features. Because if you consider a longer sequence like this is a, there will be more sequences like this because is a document is another feature, and then we can have features of 4 and even 5 words of sequence. So if we make such sequences, and they are going to be more unique in the dataset and we are going to have less representation of them, we compromise on the position related information to make this feature simple and have more representation, more frequency of these features in the documents. And we believe that for a huge set of documents, the model is still going to learn good enough. Some of the other representation schemes are, if we consider a hypothetical data set that has got diet occurring in document 1 once, sports occurring 12 times, ground 5 times, and similarly we have frequency based representation of all these set of unique features in these 4 documents, which is all we have in the data set. This can also be represented in a binary representation like this, where the words that have frequency 1 or more than 1 is being presented as 1, and all the other words or features that do not occur in document is represented with 0. This is the case where frequency related information may not be required. A particular case of this scenario would be searching for certain words in the title or abstract of a research paper. Now, if that word occurs, that would mean that the research paper is very much relevant. Irrespective of the nature, if that word occurs more than once, that would still be very relevant. So this is a case of where frequency related information is not important. Binary representation can be used, and with the help of binary representation, we can actually improve the efficiency, the processing efficiency of our system. Some other frequently used approaches are the log frequency, which dampens the higher values of frequency. So if you see uh, player, player is occurring 9 times in document 1 and 20 times in document 2, if we see over here, the difference between the two is being dampened. So as the value gets higher, its increase gets dampened, and therefore if we use the log frequency based representation, we are not differentiating between high value and very high value, because if a document has certain words occurring a certain number of time and occurring a little more would still mean that the document belongs to that specific topic. A commonly used approach for text representation is Tf-idf. In Tf-idf, the important thing is the earlier techniques that we saw so far were using the term frequency, and it adds this inverse document frequency in which a document that is that is frequent across all documents gets a negative weight. So we are only interested in words that are frequent in certain documents but not all of the document, because that would mean that these words are stop words. This is a very important approach to consider and is being frequently used. Yes, there are stop word lists that can be used to eliminate the stop words at pre-processing, but there are some corpus-based stop words as well, and this is very effective to them. So next we will look into the implementation of these techniques. Now we will look into the implementation of the text representation techniques we just studied in the theoretical part. I'll be using Jupyter Notebook for this. So let's start a new Python 3 document. We will name it as text representation. The first thing we are going to need here is to have a corpus. For the sake of demonstration, we'll use a very simple corpus consisting of only one document so that we can easily correlate the values against their features. So let's say my corpus has a document, text mining is interesting. In order to represent this data in a structured way, we are going to need the count vectorizer class from the sklearn library. So let's just import it from sklearn.feature extraction.text package import count vectorizer. We'll create an object of type count vectorizer and let's just name it as vec. Next, we are going to pass this corpus to a function of vec that is fit_transform, and that is going to convert this data into a structured format. So let's just name our structured format as x, and that is going to be achieved when we call the fit_transform function on vec and pass on the corpus to it. So now x is the desired structured data that we would like to have. So in case we want to see what we have got in x, so x is a matrix of 1 into 4, which means we have got only one row as we have got only one document in our corpus, and there are 4 columns. Since there are 4 unique features, so each feature is represented by a separate column. Let's just see what we have got in the x. So we'll pass it on to the array function, and this is the values in the matrix. There's a single row. Against each word which is a feature, we have got a frequency of 1 because all the words are occurring only once, and there is a total of 4 words in the corpus. In case we want to see what the features are, we can use the function get feature names on the object vec, and this is going to give us the set of unique features. These are the unique words that are in the corpus and are being used as features. Just to verify the number of features we can pass it on to the length function, and that is going to say 4. In case we are interested in the particular order of these features, we can use the attribute of vec, there is vocabulary underscore, and that is going to give us unique features along with their specific IDs. So interesting has got an ID of 0, which means it's the first column. Is has got an ID of 1, which means it's the second column, and the same way all the other features are arranged. Let's just add few words to it and vary the frequencies just to see its effect. So I'll say text mining is interesting. So now we will see that we have got exactly 1 row and 4 columns, so that is not affected, but this time we have got a frequency of 2 in the last column. Text, which has now got an ID of 3 and is the 4th column, has got now frequency of 2. Now we're going to add few more documents to this corpus. So our second document is text mining is like data mining, and we'll add one more document to it, and that would be text and data mining have few differences. If we execute this, now we have got 3 rows in our corpus. So we have got a total of 3 documents and 10 unique features. In case we want to see what we have got in X, so this is the X and this is our desired representation that you wanted to have. The data is now structured. If a word does not occur in a document, its frequency is 0, otherwise it's represented by the frequency of that word in that document. As we can see, most of the values are 0 because for a large corpus it's quite obvious that very few words would exist in a document, and therefore most of the row would consist of zeros. In case you want to see what the features are, so this is our list of features. Now the count would go up to 10, and this is the particular order of these features. We can also do some more operations on this corpus, and in case we are only interested in the binary values, so we'll use parameter binary equal to true, and this time now The features are going to be the same. However, all the words that has got frequency of more than 1 in a document is represented with a 1. So this is the binary representation. We can also define a maximum document frequency. If a word is occurring above this maximum document frequency, then that word is so frequent that it's more probably a stop word and we would like to remove that. As we can see, these two columns are appearing in all the documents and they're hardly going to play any role in discriminating between documents. So if we say the maximum document frequency is 2, it means any word that is occurring in more than 2 documents, just eliminate it and we do not want it. So if we execute these, we will see some of the features being cut off. And as we can see, the features that has frequency of more than 0 across all the 3 documents are being removed. The same way we can just see the number of features going down, and this is now the list of features and it has go down from 10 to 8. So 2 of the features have been removed and this is the particular order. Similarly, we can also define a min document frequency, and this time if we say 2, so a word that is occurring in less than 2 documents is so infrequent that we do not want it. It's probably a noise word and it's hardly going to make any difference. So if we apply this, the words that are occurring in less than 2 documents like this one and this one, they are going to be eliminated. And we can use any combinations of these parameters. So this is our list of features. As we can see, the words that were occurring in more than 2 documents are back here because we have removed the max condition, but with the min condition, all the words that were occurring in 1 document are being removed. We can also, if we get it back to the default, this is the default representation, we can also define the parameter max features. And max features would say that give me the best 4 features. So if the value is 4, it means that out of the 10 features that we originally have, we are only interested in 4 features. So whatever the best 4 features are, just give me that. Now the documents is 3 into 4, and this is the representation, and these are the 4 features that are being retrieved out of the 10. As we can see, all the features are in unigram. There is only one word. We can also change it because some of the features may be in bigram. So for that, we'll have to define ngram underscore range is equal to 2 comma 2. It means that we are only interested in bigram. A bigram means that text is a bigram, then text mining is a bigram, then mining is a bigram. So we are only interested in bigram. So if we execute these lines, our features are going to be updated. Now we have got a total of 12 features. The number of documents remains the same, and this is what we have got in terms of values, and this is what we are interested in. All the features are in bigrams, and because we have said that we are only interested in bigrams, we're keeping the minimum limit to 2 and the maximum limit to 2. In case we want to vary that, as we might also be interested in trigrams, so we'll keep it as 3. So now we are allowing unigrams, bigrams, and trigrams. We have defined the range from 1 to 3. The number of features have gone up to 33. This is the matrix representation, and this is the sort of features we have got. If we would just go through it, we would see that it has got unigrams, bigrams, and trigrams. And definitely the number of features are going to increase because we are considering more versatile features this time. And if there are too many for us, now we can say max features are 10. So I'm only interested in 10 out of these combinations of unigram, bigram, and trigram features, and this is going to be, these are the 10 features. And if you would see, now the 10 best features has a combination of both unigrams, bigrams, and trigrams. In case we are not interested in frequency values, we can also use the Tf-idf vectorizer, which is another class in this sklearn library. So we'll import that, we'll just take it to the default, and this time instead of count vectorizer, we are going to create an object of type Tf-idf vectorizer. We'll keep the object name the same. If we execute the fit underscore transform function on this, it's going to give us a structured corpus with the same number of rows and features, but this time instead of frequency based representation, the representation is updated as Tf-idf representation. These values are achieved from the formula that we saw of Tf-idf in the theoretical part. In most of the cases, we would not have the luxury of creating our own document, so we'll have to use a corpus. So let's just import a corpus and see how it works. So we'll be using the corpus. So if this is our corpus, we can see that it has got documents, and then after colon it has got their labels. So this is a label data set that can be used for supervised learning. 3 of the documents belongs to the label cooking, and the next 3 belongs to the label sports. If you want to import this corpus, we'll be using the function open and provide the path to the file, which is and we'll use the function read, and this will read the data for us and provide it into the corpus. Now the corpus consists of the raw data, and we can verify that this is the raw data. We would like to split it on next line because each line represents a different document. So we will split our corpus on the new line, and let's just name it as docs. So docs is equal to corpus dot split on new line. So now docs is a list of strings. If you want to see what we have got in docs, it's a list of strings, so we can use that since it's a label data set. So first we'll have to separate the labels from the actual document. So for that, we'll define two lists, x and y. X will keep the documents and y will keep the labels. Both are of type lists. And then for doc in docs, we'll iterate through all the documents, and for each document we're going to separate the document part and the label part, and we'll keep it in local variables I and L. I for the document and L for the label. And for that we will apply the function split on docs and split it this time on colon. Next we are going to append I into X and L into Y. Now in case we want to see what we have got in X, so this is the X, this is the set of documents. There is one important thing over here, that we have got some redundant spaces, and we have to get rid of this. Before appending I into X, we are going to use the function L strip for removing all the leading spaces and R strip for removing all the rear strips. So if we apply this to X, and now we'll see that all the extra spaces before the document and after the documents are being removed. We can actually use one function for both of these strip, and this is going to perform the same operation. If you would like to see what we have got in the Y, it again has got extra spaces. Now why it's important to remove these extra spaces, because if I compare this string to a string containing cooking, it's going to be different because this is space cooking and it's different from cooking. So we'll have to do the same for L also. So we'll strip these spaces from L, and now we can see that all the extra spaces are being removed from Y as well. Now the rest of the process is pretty much the same. However, instead of corpus, we'll be using this X, and we'll pass on X to it. And since we are already using X, so let's just keep it as input underscore X. And if you execute this now in input underscore X, we have got our structured corpus, which is 6 into 41. We have got a total of 6 documents and 41 features. In case we want to see what we have got in this matrix, so this is the representation in Tf-idf values. Now let's just use a proper dataset from the UCI repository. So all these datasets are of textual data. However, if we see the type of attributes over here, it says real. It means that this dataset is already structured and the features have got their values in rare. So most probably it's using the Tf-idf representation. Similarly, this dataset has got attribute types of integer. So this dataset is already represented into a structured format and is ready for applying any machine learning technique. Since the value is integer, so it can be any frequency based representation. We are not going to use that because we are interested in raw data so that we ourselves can convert it into a structured format. If we use any of these data, they do not need any structuring because they are already in structured format. So we'll look for data sets that has got this column as empty, which means that the data set is in the form of raw text. So let's just pick a data set. If we use this is not structured, so this data set needs structuring, and let's just use this. There is a repository on Kindle. This is our dataset. We have got each document on a separate line, and since it does not have any labels, so it's an unlabeled dataset and can be used for unsupervised learning. Now our task is to structure this data. So instead of this dataset, now we'll have to use the path for the new dataset, and if we execute this, we have got the corpus in the variable corpus. Let's see what we have got here. So if we look into this, this is our corpus consisting of all the documents. Again, we'll have to repeat the same process and split all these documents on these two lines, as each document over here is represented on a separate line. So we'll just do that. And since this dataset hasn't got any labels, so this part where we were separating the document from the label is not needed anymore, and we do not have any labels over here. So we'll be using the same tfidf vectorizer from the sklearn library, and we'll pass the docs to it, which is our list of strings. So if we use docs over here and input underscore X, is the structured format of our corpus. As we can see over here, it has got a total of 166 rows. So these are the documents in our corpus, and the total number of unique features are 788. So each document is going to have a certain value for each of these columns, and these values might be 0 or any tf-idf value. And this is how the dataset is being structured. See you in the next module.